Hey everyone, welcome back to the channel. Today we are diving into context engineering for LLM agents. This is the third video in our optimization series, and I think it might be the most important one we have covered so far. Let's get into it. Let me start with something that probably sounds familiar. You build an agent, you give it a few tools, maybe 5, and everything works fine. Then your project grows, you add 10 more tools, still fine. Then you get to 30, and suddenly the agent starts making strange decisions. It misses obvious tool calls or fails tasks that it used to handle easily. If you have seen this before, you are definitely not alone. And what is interesting is that the problem usually isn't the prompt, it is not even the model. It is something much more fundamental. To really understand what is going on, we need to talk about the context window. Andre Karpathy has a great analogy. It says, think of an LLM like an operating system. The model is the CPU and the context window is the RAM. Just like RAM, it has limited capacity and everything is competing for that space. Your system prompt, conversation history, tool definitions, retrieved documents, intermediate results, all of it lives there. So imagine this, 10K tokens for your system prompt, 50K for conversation history, 30K for tools, 25K for retrieved documents, 35K for tool results. That is 150,000 tokens trying to fit into a 128,000 token window. But in that case, something has to go. And once the window fills up, the model starts losing track of what actually matters. This isn't something we can fix with just better prompting. We have to come up with a different solution. When context gets out of control, we typically see 4 kinds of failures. The first one is context poisoning. It is when a hallucination or error makes its way into the context and keeps getting referenced. That is where we are compounding the mistake over time. DeepMind actually documented this with their Pokemon playing agent. It hallucinated a game state, and from there, agent's decision just kept getting worse. Second is context distraction. It happens when the context becomes very large and therefore the model starts leaning more on recent patterns instead of what it learned during training. Databricks showed that even massive models like Llama 3.1 start losing accuracy well before hitting their theoretical limits. Third is context confusion. Too much irrelevant information makes it hard for the model to focus, so it calls the wrong tools or produces lower quality responses. And fourth is context clash. It happens when contradictory information exists in the context and the agent can't reconcile it. There is also another fascinating research called lost in the middle. It shows that models perform best with information at the beginning or at the end of the context window, but accuracy drops significantly for information in the middle. So even with huge context windows, important details can effectively disappear. This is not a bug, it is how the LLM architecture works. It gets better over time, of course, but for now, it means if we want reliable agents, we need to design around it. Why is it important now? It is because the scale has changed. Real agents aren't making 3 tool calls anymore. They are making tens or even hundreds. Each call adds more context, more results, and more state to track. So the context just keeps growing. In the previous 2 videos, we covered semantic caching, which optimizes cost, and tool management strategies, which optimizes tool selection accuracy. Now we add the next layer to our agentic system. Context engineering is about reliability and keeping our agents accurate over long-running tasks. And as the Manus team put it, most agent failures today aren't model failures anymore. They are context failures. All right, so how can we actually fix this? There are 4 core strategies that have emerged across the industry. You will see these patterns in Cloud Code, in Cursor, and in all the successful agent frameworks. They are called write, select, compress, and isolate. We are going to walk through each one. I'll show you the concept, give you a real example, and talk about the trade-offs. By the end, you'll know exactly when to use each strategy. Let's start with write. Write is about external memory. The core idea is very simple. Don't force the model to remember everything. Instead, save information outside the context window. Think about how you work. When you are solving a complex problem, you take notes, you write down intermediate results, and you don't try to keep everything in your head. Agents need to do the same thing. This is the scratchpad pattern. We can use this method for long-running tasks, anything with dozens of tool calls or lots of intermediate state, or situations where we need to preserve information across many steps. For example, Anthropic's multi-agent researcher system uses a component called the lead researcher. Before it starts delegating work to other agents, it writes its plan to external memory. Why? Because if the context window exceeds the threshold, it gets truncated. Without that external memory, the plan gets lost and the whole system falls apart. With an external memory, the agent writes once, retrieves when needed, and keeps going. Trade-offs. On the positive side, you prevent context overflow, and the big advantage is essentially unlimited storage and persistence across sessions. On the downside, you add complexity. You need to manage the external state, and you need to implement the logic for when to write, what to write, and when to retrieve. But for long-running agents, it is often necessary. Strategy 2 is select, and this one is about smart retrieval, meaning we only put into context what we actually need and when we need it. You can think about it in this way. We don't load our entire file system into RAM. We load the files we are working with. Modern code agents like Cursor and Windsurf utilize this method. They use multiple retrieval techniques in parallel. Embedding-based semantic search for finding similar code, grep for exact string matches, knowledge graphs for understanding relationships between files, and AST parsing to understand code structure. And here's the interesting part. This multi-technique approach gets 3 times better retrieval accuracy compared to using just one method, which is not a small improvement. The key insight is that different types of queries need different retrieval techniques. Now, trade-offs. Of course, we can dramatically reduce tokens with this strategy. We are talking about 82% reduction in some cases. Only relevant information makes it into context. And if we already have a knowledge base or vector database, this integrates naturally. The downside is that we need a good retrieval system. If our retrieval is bad, we will miss important information. And there is also the added latency for the retrieval step itself. But when it works very well. Strategy 3 is compress. With that, we retain only the tokens that we actually need. This involves summarization and pruning. And for that, we use an LLM to condense conversation history. That way, we can remove old messages that no longer matter and only keep the essential information. When should our system trigger compression? There are a few common patterns. Auto-compact when we hit 95% of our context window. Periodic summarization every end conversation turns or right before we do an expensive operation. There is this concept called the reversibility principle that suggests we can achieve 100 to 1 compression ratios. For example, take a 50,000 token web page, compress it to a 500 token summary plus the URL. And if we need the full content later, we can always retrieve it. Cloud Code actually does this automatically. When context usage gets high, it triggers a background process to summarize the conversation history. For this method, the benefits are obvious. We prevent bloat and we can get massive token savings. And also, if we do it carefully, we can maintain all the important information. In terms of the risks, if we are too aggressive with the compression, we can lose critical details. Besides that, summarization itself requires an LLM call, which adds cost and latency. And deciding what's important isn't always straightforward. Fourth strategy is isolate. This is about splitting context across specialized sub-agents. Each sub-agent gets a focused context window for a narrow task. Here's the pattern. Our main agent receives a complex task. Instead of doing everything itself, it delegates to specialized sub-agents. Each sub-agent works in isolation with its own set of tools and instructions. They do their work and return only a summary to the main agent. This solves a specific problem called context pollution. Imagine we need to read through a massive log file to find a piece of information. If the main agent does that, its context gets filled with thousands of lines of logs. But if a sub-agent handles it and returns just the answer, the main agent's context stays clean. OpenAI Swarm and Anthropic's multi-agent systems both use this pattern extensively. And with this strategy, we can prevent context clash because each agent is optimized for its specific task. So the system scales better than trying to build one super agent. The challenging part is, of course, the architectural complexity. We need coordination between agents, and information can get lost during hands-off if we are not careful. This is probably the most sophisticated strategy, but for complex domains, it is often the right choice. All right, so let's put this in perspective and look at what these strategies actually save us. For this, I'd like to refer to the experiment in my previous video. As we saw, if we are using all 70 tools naively, we are looking at 3,663 tokens just for tool definitions. With the right strategy, we can bring that down slightly to around 3,500 tokens, which is about 5% savings. Compress gets us to 1,200 tokens, which is a 67% reduction. And select brings us down to 646 tokens, which is an 82% reduction. And if you combine isolate with a hybrid approach, you can get down to maybe 564 tokens, which is an 85% reduction. So overall, we are talking about 78 to 85% cost reduction just by being smart about context management. Of course, this was a simplified example, but I have seen these numbers in production systems. So we have got 4 strategies. How do we know which one to use? In the next section, we will walk through 5 real scenarios and I will show you how to think about this. Scenario 1. Let's assume our agent handles 10 turn conversations. The problem is that history accumulates, old context becomes irrelevant, and we start hitting token limits. Solution: combine, select, and compress. We use Retrieval to pull in only the relevant parts of conversation history, and we summarize all turns that don't matter anymore. Scenario 2. Our agent makes 50 or more tool calls per task. Intermediate results pile up fast, and the agent needs to reference earlier steps. As a result, context explodes. Solution: write plus compress. We use a scratchpad to store intermediate results externally and summarize tool outputs before adding them to context. This way, the agent can access everything it needs without overloading the context window. Scenario 3. Our agent operates across multiple domains. Maybe it handles both customer support and inventory management. In this case, we run into cross-domain queries, conflicting tool definitions, and context confusion. Solution: isolate plus select. We create specialized sub-agents for each domain and use routing to direct queries to the right agent. This way, each agent operates with a clean, focused context. Scenario 4. Our agent processes large documents that exceed the context window, and we can't just chunk them without losing coherence. Solution: compress plus write. We summarize document chunks intelligently, store the full documents externally, and when the agent needs more detail, it can retrieve specific sections. Last scenario. Our agent works great initially and then starts failing, and we are wondering what happened. This can be the classic context poisoning. A hallucination entered the context, and now the agent keeps referencing that wrong information. Solution: add error handling to catch bad information before it gets into context, use compression to periodically clean out potentially corrupted context, and implement validation checks. Before we wrap up the framework section, let me give you 4 production patterns that work across all these strategies. First, self-healing. When a tool call fails, catch that error and feed it back into context. LLMs are surprisingly good at reading error messages and adjusting. To keep your agent from getting stuck, set a simple rule. For example, 3 strikes, then escalate to a human or reset. Second, context budget monitoring. Track token usage at every turn. Set auto-compact triggers at 80 or 90% of your limit, and don't wait until you hit the ceiling. Third, tool response as prompt engineering. Structure your tool output carefully. Use XML or JSON, add metadata hints, include inline instructions in the response itself, and remember, the way you format tool outputs shapes how the agent thinks about the next step. Fourth, hybrid approaches, meaning you don't have to pick just one strategy. For example, select relevant documents, compress conversation history, and isolate complex subtasks. This is the strategy that real production systems usually use. Now let's bring this all together and go through 4 key takeaways. 1. The context window is a scarce resource, just like RAM. Treat it that way and don't waste it. 2. You have 4 strategies. Write for external memory, select for smart retrieval, compress for efficiency, isolate for specialization. 3. Most agent failures are context failures, not model failures. So when your agent breaks, look at the context first. 4. Start simple. For example, you can begin with select and compress, which give you the biggest wins with the least complexity, and then add write and isolate when you actually need them. This was the third and for now the final video in our agent optimization series. We started with semantic caching for cost optimization, then tool management for tool selection optimization, and now context engineering for accuracy and reliability optimization. With each video, we tackled a different bottleneck, and together they give you a complete framework for building production-grade agents. If you haven't watched the other 2 videos, I'll add their link in the description. All right, that's it for this video. If you found this helpful, don't forget to subscribe. Thanks for watching, and I'll see you in the next one.